All right, so this is our last day of notes in chapter 6, and we're talking about the logistic model. So just a quick bit of review here. A rate of change of a population is proportional to the population. So the rate of change, which is dp dt, is proportional, meaning some constant k, to the population, so times just p. And if we want to get the general solution to this, we can divide p to the left side, multiply dt to the right side, separate, integrate. This would be natural log of p equals kt plus c. Base e both sides. So p is equal to e to the c is c times e to the kt. All right, so this is just kind of what we've been working on in chapter 6. And a lot of times with the population, populations don't just grow without bound. At some point, the populations level off. So that's where this logistic curve comes into play. You've got exponential growth for a while, but at some point, there's a point of inflection where the population stops growing quite as fast and it even levels off. So we call that leveling off point the upper limit. And the function won't grow past that. That's also, the upper limit is also known as the carrying capacity. It's the maximum population that can be sustained. So here's something to memorize, sort of the format of. The logistic differential equation is equal to, dp dt is equal to k times p. So you've got something that's directly proportional to population, but it's also times 1 minus p over L. If you have something in this format, you can see that L is the carrying capacity, which means that L, that denominator there, is the highest value that the population can hit. This horizontal asymptote is the value L, which again is the carrying capacity. Right? So how do we come up with the general solution to this? Now, we could integrate every single time, but you could see we're going to go through how to integrate this. It'd be so much easier if you just sort of have the differential logistic equation memorized and then also have the logistic model memorized. So let's start deriving that. Okay, so we're going to take dp dt, and we want to, actually, let me write this down here so I have something to reference. So we want to start here. Now, the only variable in this equation is p. K is a constant and L is a constant. So when I'm trying to separate my variables, I'm going to divide dp by both p and 1 minus p over L. That leaves me with k times dt. So we've done separate. Now, before we start integrating, there's kind of a trick that we're going to work on here. U sub is not going to work in this case. And if I distribute through the denominator, that's not going to help me either. I'm going to have something I still can't integrate. So I would like to separate this out and figure out, well, what two fractions add up to give me 1 over p times 1 minus p over L. So let's do that work kind of off to the side over here. All right, so let's start here. We have 1 over p times 1 minus p over L. Let's get rid of this complex fraction here. So let's say we multiply by L over L. That makes this, let's go down here. That makes this L on top. And then I'm going to distribute the L through here. So that makes this p times L minus p. All right. And there's kind of this trick. We're going to get into this in a later chapter too, but there is a trick for how to separate out and figure out what two fractions are being added together to get this. It's something over p times something minus L over p. And again, you won't be deriving this every time, so I will get more into this in a later chapter. But the idea is this. You can sort of figure out, if I were to plug in p equals 0 to this and plug in p equals 0 to this, I would get L over L. And so when I have the fraction that just has a p in it, L over L is 1. And if I were to plug in for a second time, if I were to plug in P equals L, there and there, and I cover up this L minus P, I get L over L again. So I get 1 here. Now you can double check the math on this. Does the math actually work out? If I add these two fractions together, L minus P plus P over the common denominator, you do get L over P times L minus P. So I don't want you to stress about this cover-up method. This is not something you have to do for our test right now. It is something we'll do in Chapter 8, but we're not there yet. Okay, so all of that was just to get me to set up something that I can integrate a little bit easier. So instead of dp over p times 1 minus p over L, we're going to make this 1 over p plus 1 over L minus p dp equals k dt. Now we can integrate. So before I couldn't integrate this, but now I can. I can integrate 1 over p. That's natural log of p. Careful with integrating L minus p. U is L minus p. Du is negative 1. So I'm going to have to put in a negative here. So I should get minus the natural log of L minus p equals kt plus c. Right? With natural logs, we want to get rid of them. So if I have two natural logs, I want to condense them down. This is the natural log of p divided by L minus p. Now I can base e both sides. P over L minus p equals c e to the kt. Right? And, oh, wait a minute. Sorry, there's one step I wanted to go back and do. So that our formula is nicer to memorize and doesn't have a negative sign in it, there's a little trick I want to do to this. I want to multiply by negative 1 on both sides. I want the division to be in a different order. If we do that, it makes this the natural log of L minus P divided by P equals negative KT plus C. Then we can base E both sides. L minus P over P equals CE to the negative KT. You need a negative exponent for your logistic model. All right, solve this for P. I've got to multiply P out of the denominator. Get the P's on the same side. Factor out a P. And divide. So P is equal to the carrying capacity divided by 1 plus CE to the negative KT. So we kind of went through a proof for how do we go from the differential logistic equation to the logistic model. And you can see it's a pain to do by hand every time. So just memorize these two things. You will be told in the problem that something is logistic, and that will trigger, hopefully, your memory to use one of these models. Okay, so here's an important thing that they like to throw at us. When you're looking at the logistic model, which again is this, the point of inflection here on the logistic model, the point of inflection is also equal to half of the carrying capacity. That's always where it's located. So a lot of times they'll just ask us what y value that happens at. It's also known as the place where you have the fastest rate of change, the fastest p prime, basically. So they might say find the y value at which you have the fastest rate of change. You should know then that that's just half of carrying capacity. All right, so let's do some problems. We're going to use our calculators for these. A state game commission releases 40 elk into a game refuge. After 5 years, the population is 104. I'm just going to make note of that as an ordered pair. The commission believes that the environment can support no more than 4,000 elk, that's carrying capacity. The growth rate of the population in years is this. So this is a logistic differential equation, right? And they gave us this little model here. Write a model for the elk population in terms of T. So go back to this page. I'm sure you don't have this memorized quite yet. We're trying to get a model that is P equals L over 1 plus C e to the negative kt. This is the goal. The goal is to know a value for L and C and K. We know L already. L is 4,000, so we do know that. And we're given an ordered pair here. So the ordered pair represents a T P value. So let's plug in what we know so far. Oh, there's one other thing. 40 elk were released. So the T and the P that I want to start out with is always the T equals 0 because that will be easier. So let's plug in 40 for P. L is 4,000. 1 plus, we don't know C. We know e to the negative k times T was 0. All right, well, this is really 40 equals 4,000 times 1 plus C times 1, right? E to the 0 is 1. You're trying to solve for C, so multiply 1 plus C over to this side, divide 4,000 by 40. So that's 400 divided by 4, that's 100. So we've got C. C is 99. So start building this equation a little bit further. We've used this first order pair. Now we need to use the second one. So now we know that 104 is equal to 4,000 over 1 plus, now we know C is 99, e to the negative k times T is 5 in this one. Go through and solve again. So 1 plus 99 e to the negative 5k equals 4,000 divided by 104. Subtract 1. Divide by 99. Natural log both sides. And solve for k. Now you want to avoid rounding numbers, so that's why I'm not bothering to type any of this in yet. If they're just asking me for the model, maybe I'll report what this decimal is, I guess. But it's best to leave it to as many decimal places as you can. So what was that? Log of 4,000. Let me split screen here so I don't type it in wrong. Divided by 104 minus 1. I'm going to get that answer because the divided by 99. Oh, no, the divided by 99 is in there. Okay. Log of 4,000 divided by 104 minus 1. Get that in parentheses. There's the numerator. Divided by 99. All of that's in the natural log. Okay, so I'm getting this value here. And then when we plug that back into our equation, oh no, we can just leave that as our, sorry, it wasn't asking us to find anything. Okay, so we can say that, hold on, let me do that in steps to make sure this was right. So that was 4,000 divided by 104 minus 1. Yes, and then, oh, I never divided by 5. Sorry, this is negative 5k equals this. There we go. That's why my answer wasn't matching up. Okay, divided by 99. Natural log that answer. Divide that by negative 5. There we go. That's better. So 0.194-ish is our k value. Now, the model that I would write is P equals 4,000 over 1 plus 99. Now, I would just leave like this k value like this, but if I just want to write the model, make sure you put the negative in here, be negative 0.194 t. But I would want to leave that on my screen so that when I find the population after 15 years, I'm not rounding it off. And maybe you store this, like store this as X, so that when you go to type in what is P of 15, I can just sort of carefully say, all right, it's 4,000 divided by 1 plus 99 e to the k is the x value I just stored times 15. That's like my most precise value here. Oh, wait, what just happened there? 1 plus, oops, I forgot a negative. Can't only have two deer in there. It's negative k. That's better. 628 elk, I guess, is this problem. So I would round this to the nearest elk, so 629 after 15 years. Find the limit as t approaches infinity. So the limit as t approaches infinity of 4,000 over 1 plus 99 e to the negative kt. It doesn't really matter what k is. Now pay attention to the negative exponent. It's probably better to write it like this. 99 over e to the kt, because when you're plugging in infinity into that, you're getting 4,000 over 1 plus 99 over infinity is practically 0. So 4,000. Now, did you have to do the math on that? No, because remember, this is logistics. So this is the carrying capacity L. All right, let's look at an AP question. Now, be careful on this AP question. If you look at parts A versus C, notice how the equation is the same thing. They've just traded out variables. So read the question because this matters. A population is modeled by a function P that satisfies they're telling us this is a logistic differential equation. So what I can gather from that is I have this set up so that there's some K value, which is 1/5, times P times 1 minus P over L, right? Go back a page or two if you need to. This is our setup. So we can see the denominator right here is the carrying capacity. So for part A, if P of 0 equals 3, what is the limit as t approaches infinity of P of t? That's equal to L, and L is equal to 12. So I would just say the limit as t approaches infinity of P of t is equal to 12. The P of 0 equals 3 doesn't matter. If P of 0 equals 20, what is the limit? Same thing. So I guess I should say this is for P of 0 equals 3. And for the second part, same thing. For P of 0 equals 20, it doesn't matter where you start. The carrying capacity is still going to be L, which is 12. So it's 12 no matter what. For part B, if P of 0 equals 3, what is the value of P? For what value of P is the population growing the fastest? Remember, that's at the inflection point. So P of T has fastest rate, growing the fastest, at points of inflection, which occurs at 1/2 of 12, or 6. What value of P? P equals 6. Now, part C says a different population is modeled by a function y that satisfies the separable differential equation, not logistic. That means that this is not just carrying capacity and whatever. This is just a separate, integrate, celebrate scenario. Find y of t if we have this initial condition. So we need to divide y to the other side. I'm going to leave the 1/5, 1 minus t over 12 dt to that side. Integrate. Natural log of y equals 1/5. Let's see. So 1/5, when you integrate when you integrate 1, you get t. When you integrate t over 12, excuse me, you get minus t squared over 24. plus c. Maybe we should distribute the 1/5 through it. I guess that might make it easier. Base e both sides. So y equals e to the, let's do that, 1/5 t minus t squared. 5 times 24 is 100 plus 20, so 120 times e to the c, right? So y equals c, e to the, 1/5 t minus t squared over 120. Plug in the condition 0, 3. So y equals 3 times e to the t over 5 minus t squared over 120. That's our model for part C. For part D, for the function y, what is the limit as t approaches infinity? Again, it's not just carrying capacity. We have to actually do the limit. So we're finding the limit as t approaches infinity of what? We've got 3 times, now think about t over 5 minus t squared over 120. When you plug infinity into that, you're basically getting negative infinity, right? The end behavior on this graph is like a parabola that opens down. So these exponents are just going to get more and more negative. 3 to the negative infinity is the same as having 3 over some huge number. E to the negative infinity is the same as having 3 over some huge number. So that limit is 0. All right, the homework for tonight is to work on these problems. This is just kind of practice with a little bit of logistic problems. I'm not checking this, it's just practice. And I think we also have homework. This out of the way. Homework is, finishing or working on Euler's packet early if you want to. Otherwise, we're doing that in class on Monday. All right, that's it for this set of notes. Come see me if you have questions.